This chapter, the main point is fractal universe. Or maybe I show this one first. Something like this, you have seen, right? This is called fractals. You see a structure and then zoom in, and then you see the same structure. So for example, you see this kind of, structure, and then zoom in, and then you actually see the same structure. These kind of things are called fractal. Maybe you have seen something like this in art or something like that. But then today's main point is universe is also like this because of inflation. And then more importantly, I want you to understand why. Okay, that's the main point of this chapter. Okay, so let's get started. How do I close it? Okay, here. Okay, so let's get started. So we look at inflation, and then we learn that the inflation can create the clumpiness of the CMB. This is initial density fluctuation, right? Remember you from the Hawking radiation, whatever at the event horizon, one of the photons inside the event horizon comes towards us, outside the event horizon would disappear outside of the horizon, and then that happens from quantum fluctuation or through pair creation. So the fluctuation of the universe, or CMB, is quantum fluctuation, which is Gaussian, that we learned from inflation, right? Then this happens along the inflation. So at the beginning of the inflation, universe is very small. So at the very small scale, this fluctuation, quantum fluctuation happens, right? And the universe becomes a little bit bigger, and then event horizon becomes a little bit bigger, and then at that scale, quantum fluctuation happens again, right? And then a little bit later, universe becomes even larger, and then that larger scale, again, there's an event horizon, so quantum fluctuation happens, right? So in various scales, this quantum fluctuation happens. So in such kind of situation, it's more convenient to use a Fourier series to describe the Fourier fluctuation. Have you heard of the Fourier series, Fourier transformation? Maybe you did. Okay, good. You guys are good. Okay, then maybe it's easier. We just probably go through what maybe you learned in other math class or something. Okay, then if you expand Fourier series, this fluctuation, we can describe small scale, large scale independently. So that's more convenient. So let's go through this. Say rho bar is average density of the matter, and then delta rho is a deviation of fluctuation. And then if you delta rho over rho bar is going to be fractional over density. Sometimes it's just written as delta, okay? Then in this case, in the universe, this delta average should be 0, okay? Fluctuation should be in the middle, it's average, right? And then L is a length, and then we first think about one-dimensional universe, so that we just have L and X direction. And then delta X is, by definition, delta rho by rho equals, we can describe this using Fourier series like this, n equals minus infinite to infinite and ckn e ikn x. So mathematically, we can do this, and then these, each n, it corresponds to each modes at the different scales. Okay, so a fluctuation can be written in a Fourier series, and then here Kn here is the 2 pi n divided L, and that's called wave number in a Fourier space. Then you can this Ckn is written down. You can be written something like this: 1 over L integration is minus half L to plus half L, and then delta x and eikx dx. And then these are coefficients, right? So this is this, okay? And then this C, this coefficient C tells you how much structure there is at a particular scale of n. Okay, so in that scale, spatial scale, how much fluctuation is there? That gives you. So, okay, that's Fourier series, Fourier expansion of the fluctuation. And then now three dimension is the same. We just make this k and x, or in this case r, as a vector. So now it's a vector instead of x. This is vector. Well, actually it's kx, ky, kz, but it's the same thing. It's same thing. You can expand it in the same way as one dimension. Okay. And then we can think about how much variation is in Fourier coefficient, that is C. So variation, you can write it down something like this, and then this is this. Okay, it's standard deviation, or root mean square. And then if delta x is isotropic, inflation is isotropic, then this coefficient Ck doesn't depend on direction, any direction. Well, inflation is uniform in all directions, so we don't need to think about particular direction. And then what we call this fluctuation, this as a function of wave number or scale or n, is called power spectrum, which is pk. Power spectrum is basically this one. How much variation in Fourier coefficient. Okay, so that's how to describe the fluctuation of the universe, right? And then in a present universe, for example, we have something called gravity. Okay, so if this fluctuation is positive, that means high density, right? So then if high density, there's a gravity, so the fluctuation or density is going to increase. And then if low density, there's less matter, so less gravity, so this delta density is going to be even less, because there's no gravity, so matter around low density is going to be attracted to somewhere else with high density. Sometimes we call it void. So nowadays high density places are even getting higher density. Low density places is even get lower density because of the gravity. So one good thing, one very convenient thing is these happen in linear. What I mean by linear is this evolve from self-gravity, so that Fourier modes evolve independently. So that's why power spectrum is convenient in cosmology. So, it's a linear regime. So, largely each scale is independent. Large scale is large scale, small scale is small scale. They don't, interact too much. So it's very convenient in cosmology. When you have a power spectrum like this small scale and then large scale are independent. So we just think about each scale independently. So that's very convenient. Anyway, so this gravity is nowadays in the universe. During the inflation, we can just ignore the gravity because inflation is so much more powerful than the gravity at that time. Okay. So we can just ignore the gravity during the inflation. So what is it? Gravitational potential from inflation is invariant under time translation. So after some time later, universe looks the same. So there must be constant level of fluctuation. So that continuous time invariant process in which quantum fluctuations created and inflated out. So no characteristic length scale. So that's why universe becomes fractal. So actually I already explained a little bit. So when the universe is small, say this is event horizon, and then in small scale, there's a fluctuation, right? And then later, universe becomes larger, right? And then in large scale, say this is event horizon, in large scale, there's a quantum fluctuation here. And then even later, the universe becomes larger, and then this event horizon becomes larger, and then from this event horizon, there's a quantum fluctuation. So during the inflation, along the inflation, the event horizon becomes larger, right? And then at each scale, there's a quantum fluctuation. And this quantum fluctuation is the same Gaussian fluctuation. So at any scale, if you look at the universe, you have this Gaussian fluctuation. So that's like a fractal universe. At any scale, fluctuation is Gaussian. So what does it mean in terms of power spectrum? Well, we spent a little bit of time to look over, review the power spectrum. So what that means in power spectrum is it means it's flat like this. So this is, as a function of k, the power spectrum. So this is how k is a scale, right? In each mode, in each scale, how much fluctuation is there is power spectrum. So at any scale during the inflation, the fluctuation is Gaussian. So in any scale, the fluctuation is the same. Pk is the same. It's constant. So this is what inflation is going to predict. Okay? So that's a prediction from the inflation. And then now, do we want to see the data? Is it really constant? So this is prediction from inflation, right? Let's look at data. Here, the data points are, these are data points, with error bars. And then it's basically flat, right? As predicted. Well, actually, I don't know. Actually, this is very simplified here. If you think more detail, there's a little bit of slope like this black line, but basically it follows the fractal universe, constant power spectrum. Isn't it amazing? You know, like this is inflation theory predict that power spectrum is flat, and then we observe power spectrum and it's flat. But by the way, this is looking at a very large scale of the universe. This is CMB power spectrum, but if you go smaller scale, there's a CMB fluctuation power spectrum. That part is affected by gravity and astrophysics, which I will explain probably next week. So that part is not flat. We are looking at a very large scale where things are not affected by gravity or something, gravity or astrophysics. Okay, that's another, you know, beautiful part of the inflation theory. And then here, just a little bit note about the power spectrum. So here, power spectrum we use in cosmology, we use a natural log power spectrum. Because if, you know, K, these modes, if we do it like K1 is 1 over 1 meter, K2 is 1 over 2 meter, then if you define it that way, linear way, it depends on scale, right? 1 meter, 2 meter, this depends physical scale. And this physical scale, as you know, it's changing with the expansion of the universe. Scale changes with the expansion of the universe. So it's more convenient to use the natural log. So K1 equal K, and K2 is 2 times K, and K3 is 3 times K. If you do it, take the axis like this, then with the expansion of the universe, K becomes 2 times larger, but everything else, K2, K3, also becomes 3 times larger. So it's more convenient to describe the expanding universe. So we just use natural log for the K. Okay. Then if you do that, then we take you know, we define a K that the log ln K is constant. So in this case, maybe this is 2 or something like that. That's more convenient. Okay. Then we can, you know, describe this is spectrum becomes scale invariant. Sometimes called this is called Harrison-Zeldovich spectrum. And then this and then we describe this one. Where is it? This one. So if you take the log K, then we call it a dimensionless power spectrum. Okay. Okay. Then how do we relate this dimensionless power spectrum to power spectrum? Do I need to do this? Do you want to do this or? Okay, so okay, I'm going to skip all these derivation because I think it's very boring. Is it okay? Then I just focus on an important part. Okay, so okay, here. So I just jump to the conclusion. So this is power spectrum pk. This we talked about, right? And often we write it as k to the power of ns minus 1. Okay? And then this is dimensionless power spectrum, which is, divided by log k. Which is, there's a relation. Then if you write this like this, then it's become ns plus 3. Okay? This part, this derivation is the part that I skipped, but if you follow that, you get 3 here. Okay? And then you get 3 here. Okay? Then now this ns is important parameter to talk about inflation. Ns is spectral index of scalar perturbations. Okay, that's of course. And then ns equals 1, that's for perfect case, scale invariant spectrum. And ns equals 0, then it's just noise. Okay, then this ns can be measured here. Okay, so here there are various inflation models. So we talk about inflation's potential, inflation field's potential, right? And it can be, you can think about, because it's unknown now, you can think about whatever shape you like. You like 3, you put 3. You like 2, you put 2, because we don't know yet. Then you can write this. You can derive various kind of inflation models, and then this is ns that we're talking about. It's a tilt, right? Tilt of the power spectrum. And then this is tensor to scalar field. So that means this I will talk about probably in 2 weeks from now. But this is how strong is the gravitational wave background from the inflation related to energy of the inflation. These things we can measure, right? These things. Because this we measure from beam multiplication, which I talk about in 2 weeks. And this one actually I talk about, this is the tilt of the power spectrum, right? So I said it's going to be flat, but then it's not perfect flat. There's a little bit of tilt. Then we can measure this ns. So if it's 1, it's a perfect flat, right? It's perfect flat. But actually there's a little bit of tilt. So in this case maybe 0.96. Then we can constrain inflation models through this. Okay, so I don't know. So if it's 0.96, this red one, which one is the red one? Red one may be 2/3, be potential 2/3 inflation model, maybe more suited to here. Something like this. I'm sorry. The red one is here. This curve is observational constraint from Planck, polarization from W map, and then high L power spectrum. It's something like this. Also, actually, if the observation is within this red, then this model is ruled out, right? It's outside, right? Okay, and this answers Suyun's question that how do you constrain epsilon and eta, the parameters of inflation models, because epsilon and eta also decides this. So you can constrain that. Where was it? Something like this. So something like this, the slope of the power spectrum is related to something like this, to eta and epsilon. So, and then this you can measure observationally. So through these kind of relation, you can constrain eta and epsilon of inflation models to some sense. Okay, so this is how, well, it's difficult to measure inflation, but there are some hints we can get through observation. I feel I'm confusing people. So well, this I don't go to much details, but maybe you can just hear that as a story. So two other key predictions of inflation is perturbation of matter and radiation should be equal. So at the end of the inflation, with the friction, the potential energy of the inflation becomes a radiation in the universe, right? This is called reheating, right? And this potential energy becomes matter and radiation in this universe equally. So this inflation is adiabatic perturbation, is perturbation. Okay, that's a prediction from inflation. So this matter and the radiation created equally. Then this we just talked about, but the phases of Fourier are uncorrelated. So small scale, large scales are uncorrelated, and it's random to each other. So it becomes a Gaussian random field, which so far almost consistent with observation. Then we talk about, let's review the inflation predictions. So Gaussian random fluctuation, because it's a quantum fluctuation, it's a Gaussian, and then Planck satellite, CMB fluctuation satellite, measured Gaussianity, and this is very small number, 2.5 plus minus 5.7. So it's almost perfect Gaussian. It's actually consistent with zero, right? This F and L is a deviation from Gaussian, and it's consistent with zero, right? And this is very small value. So far, this Gaussian fluctuation is consistent with inflation. Spatial flatness, as we saw many times, it's almost flat, this universe. Gravitational wave background is predicted by inflation. This probably B mode fluctuation will be found very soon. And the adiabatic fluctuations, it's consistent with CMB. So far, these inflation theory are consistent with observations so far. And then this again will be prove the final missing piece is this gravitational wave background through B mode polarization. So that's why a lot of people are trying to detect this B mode polarization. By the way, I invited an expert on this gravitational wave background, Professor Hazumi, on May 1st. It's Thursday for a lunch talk here in the same room. So if you're available on Thursday lunchtime, I encourage you to come here, listen to his talk. He is doing two things. One is a light burst satellite, satellite to detect this gravitational background, and another one is a another CMB polarization telescope in Chile. If we detect this, he also gets Nobel Prize. So maybe we should listen to him before he gets a Nobel Prize. It's May 1st. Okay, then. So this is it's almost finishing, but it's interesting to think that. So we talk about throttle approximation, and then our particle need to be near the local minimum for the inflation to finish, right? So that this oscillation stops. But for example, if your universe is very, very far from the minimum, so minimum is something like here, and then your universe is very far from the minimum, and then your universe may be inflate forever. If you're going through a very long slope and then there's no end, then your universe might inflation forever. That could be possible. There may be another universe or another part of the universe that's inflating forever. That's theoretically possible. If we are born in such universe, then there's no Earth or no star, no galaxy, no Earth, no human. So maybe we're lucky that when our universe was near the minimum of the potential, so that inflation ends, and then our universe our universe can create galaxies and stars and Earth. Yeah, I mean, what's fun to live in a universe that's inflate forever? Everything is okay. So I think that's the end of this chapter. Okay. And then maybe Delian has found another Death Star presentation, right? Yeah. So can we try to watch, maybe just for fun? You gave me the link?
Yeah, in the cosmology report, instruction.
Instruction?
Yeah.
Here?
Yeah, in the bottom. In the example part. This one, Star Wars, Death Star.
This one?
Yeah.
Oh, thank you very much.
This is
I'm going to run twice. Good morning, I'm Ethan, and today we're going to talk about the scenes in Star Wars, which is possible in reality. So we first show the clip of Star Wars.
I mean, is he the one talk about? The first one?
Yeah, this is from Joss, and there is another group using cookies like you said. I put the link to.
Okay. So, but then this have 26 minutes.
Sorry, we can show the clip.
So which part?
Problem?
If you want to see the cookies part, you can jump to the other link.
Not this one.
Not this one, but they use the same Death Star. This one.
This one?
Yeah.
Okay. Thank you very much.
So you can jump into.
Okay, hello everyone. So we are from Group 12, and my name is Ika. So for our final presentation.
So where should we go?
You can jump into 31.
31 minutes?
So 30, from 30.
Something like
so
this?
This guy, yeah. After this guy, they explain the cookies part and something.
Okay.
Yeah.
Here?
One. Yeah.
Oh, this is same topic, no? I mean, this Aldebaran is the planet, right?
And I will continue. I will be talking about the instantaneous vaporization of the planet called Aldebaran. So I'll show you a brief example of how the clip is. So you can see this movie was very old, and then they didn't consider much to thought, and then we can see how the laser just shoots a planet, and then it just vaporizes. So the planet disappear without any debris. And then If I count it correctly, yes, it is correct. It's only 1 second from the time that the
You said 2
laser beam
seconds.
hits the planet and then it disappears. And how to go back to? I'm sorry. Okay, so my claim is that this scene is an exactly exaggeration. Why is that? I will shortly explain to you guys. So we will understand briefly about how it works. So here in my calculation, I consider two things. It is the initial heat where it's like a boiling heat, to the initial heat to the boiling heat, and also the heat of latent where where the heat of an object transforms into evaporation, and I combine it in here, and I consider the planet using the Earth, so assuming that it's all in the mass of Earth, specific heat capacity of Earth, and the T boiling and T initial from 300 to 2500 Ks. And then the next thing is we calculate each from the boiling initial point to the boiling point, and then we will get the Q heating total of that amount, and the Q evaporation is that amount. Then we add up together to know how much of the total power is, and then we will get 2.54 times 10 to the power of 31. And what this tells us is that the power output of the sun we can compare to is 3.8610, that number. And then if we average the ratio, it will be 65,000 times the amount of the power sun in 1 second to destroy a planet. And realistically speaking, there is no such amount of energy or device right now that can produce 65,000 times from the amount of the sun power to destroy a planet directly and vaporize. And there is also the thing called beam of divergence, where this calculation I did not consider any distance, so it is directly with zero loss of initial from the beam. So the beam is considered not from the movie distance, which will make it more unrealistic, because, do you understand what I mean? Like in the scene there was a distance from the laser to the planet where I did not consider that, so it should be less than that, the power. It should not destroy the planet completely and vaporize. And then I have an example video, like I did not, of course my hand does not have heat, and then I will target the initial point in the middle here. I will break the cookies to show you how it takes time to break a planet. It doesn't instantly disappear like magic. So I will put the stress and weak point in the middle, and it will represent the laser that was shot to the planet. And then you can see while I press it, there is a snap in between the middle where it's the weakest point due to the stress concentration where I press it, and when I continue to press it later on, you can see how it breaks slowly apart. It cracks a line, it cracks a pattern there. So it takes time, and it does not vaporize, you can see, and there is a debris. Where they did not show the debris at all in the movie. In the movie, they just show it disappears. And then I will show you the last one is the pattern here, where the pattern is a stress line from the point of pressure, which again it wasn't depicted in the movie. And before my conclusion, so this is another gravitational binding energy. Why is this for? This is just to calculate how much realistically for the planet to completely destroy it in the space, which is 6.8 days from this calculation, which is not 1 second, and again it's unrealistic. And my vocabulary is the beam of divergence, which means that the amount of intensity lost during the travel time of a beam. Okay, thank you. Do you have any questions?
Oh, interesting. So she calculated some energy to make it evaporate, but the order was very similar, no? So she calculated this boiling energy and the evaporation energy, but then order was 31. I think Suyun's order was 32. So actually order is very similar, I think. And then later she quickly showed this one. This is Suyun's the same calculation, no? gravitationally bounding energy. I want, is it 32? Well, this is the same number, no? Oh, so you guys' calculations agree. That's good. Okay. Anyway, it's interesting to see. Okay. Okay, so it was short, but then that's the movie that we talk about. What should we do? We still have 20 minutes. Do you want to listen to more? I thought the video was longer, but it was very quick. Should we do that? Okay, maybe I just talk a little bit about this. Okay, this is, you can just relax. This is just another formalism, how to describe this. So we talk about angular power, we talk about power spectrum, right? It's a root mean square as a function of angular scale. But actually sky is not flat. It's sphere, right? So we need to describe it, this spherical harmonics. This YLM. So instead of that power spectrum that we're talking about need to be in this kind of shape, you know, spherical using this spherical harmonics, and then modes with angle. Okay, I am going to skip this, but then you notice that instead of xy now, you know, we have theta and then phi, you know, angular scale, because sky is sphere, and then you expand it like this, and then this is called associated Legendre polynomials, and this is corresponding to, you know, from n equal 1 is monopole, 2 is dipole, 3 is quadrupole, octopole. It's like this. Maybe you have heard of this, right? And it's like electron orbits in atoms. Maybe Baldwin is more familiar with this. If you learn quantum mechanics, you learn something like this mode, right? It's monopole, dipole, quadrupole, octopole, like this. So it's the same thing. CMB, cosmic microwave background, it can be like this. And then what for CMB, we talk about the temperature difference, right? Then spherical Fourier transformation is going to be something like this, depending on the angular direction, theta and phi, and then expand it, and then, yeah, okay. And then in this, if you write it in spherical function, then this ALM instead of C is a coefficient, and this is a Fourier coefficient, and then it can be written something like this. Okay, then 90. Then orthogonality is, you know, if you integrate sine and sine x and sine mx and sine mx, when mn is not the same, it's always 0. So these are not correlated. Then it's the, if you write it like this with y, if L equals not L dash and M equals not M dash, then it's 0. Okay, this means it's independent. Each modes are independent. So, and then also this coefficient doesn't depend on M, so isotropic. In any direction of the universe, it's the same. Fluctuation is the same. Okay. And then so in here, instead of K, we're using L and M. These are the wave numbers on the sky. So this is in Fourier space. So if L is large, that's smaller spatial scale. And if L is small, we are talking about large scale. And then this is something convenient to remember. If L is something like 180 degrees divided by theta, so say L equals 1 at 180 degrees. That's something to convenient to remember. And then power spectrum is the same, right? So CL is this average of this A. We can do it, write it the power spectrum, and then okay. Then what's next? Okay, then we can plot power per log L. Again, it's log L because it's a scale invariant, and then it becomes flat. Okay, and then this is for research. This becomes a problem, but only 12 plus M samples on the sky. So this, gives us cosmic variance. So it's a problem. So for example, if we want to sample, 180 degrees, there's only one data point, right? So here's a 1U, and then there are only 180 degrees direction. Say, if it's 90 degrees, there are many 90 degrees points, right? But if you go to 180 degrees, there's only one. So that limits the measurement because we only have less data at the large scale. That's called cosmic variance. This is a problem. We only have one universe. We need a lot of universe to measure it large scale more accurately. Okay. And then, for observationally, Kobe, which got the Nobel Prize, Cosmic Background Explorer, in Nobel Prize in 2006, measured the angular resolution is something like 0.1 degree. And then, actually this I showed it earlier. So these two guys got Nobel Prize. Okay, actually I showed this earlier, but it was not really correct because it was already spherical power spectrum. So, and then I show you it's flat as predicted by the inflation, right? And a WMAP, which improved the spatial resolution to 17 arc-minutes. So that's much more higher resolution than Kobe. So that's why you can measure the small scale. But then at the large scale, so here, this part is this part. This part is this part, that part, and then this is basically consistent with the flat. Well, this part, you're affected by other astrophysics, so it's not flat. Okay. Sometimes people call it this Zach-Swoffer plateau, and then this is the part that is scale invariant. And then this fluctuation, I think I will explain next week. This is also another very interesting part where we can measure cosmological parameters. Okay. I think that's all. Okay. Okay. Maybe we stop here. And next week, today there are a lot of equations, so it may be, I was worried it may be boring to you. But next week will be interesting. Next week I will explain where these fluctuations came in the CMB power spectrum. And then this is a treasure. We can learn a lot about our universe from this fluctuation. So that's next week will be interesting, I think. Okay, so maybe it's time to stop. I thought I forgot whose turn. Is it your turn? Okay, okay. So please prepare your presentation. I look forward to them. Then, if you have any question, you can ask me or come to me. Okay. If you don't have question, let's stop here and then see you next week. Okay. Thank you, Suyun, again for a good presentation. That's very interesting.